Right, so I'm talking about TensorFlow and specifically TensorFlow from Haskell. And really, I'm just talking about what I know about it, which is really just the early days. I'm not using this in anger. I've just kind of been kicking it around on a few weekends here and there. And so the reason for this is that I do machine learning and data science as my day job. And that means that you tend to be using all this Python stuff for machine learning. That seems to be the dominant way of doing things. I think even Nick had some Python code in his Databricks notebook over there. So Python's really dominating this area, but there's a few things that can be quite frustrating about Python because it's dynamically typed and got a lot of other sort of weird quirks about it. And a lot of those are reasons why, the opposite of that anyway, are reasons why I like Haskell. So first of all, just a show of hands who's heard of TensorFlow and has a vague idea of what it is. Okay, so yeah, open source machine learning, mainly used for machine learning. It's developed by Google. It's focused on graph-based numeric computation, and it's one of the drawcards is it can do its computations on CPU, GPU, or even application-specific integrated circuits like TPUs, the tensor processing units. And like I said, mainly used TensorFlow, like many of the others. Most people who are using it are using it via Python. Most of the sort of performance-specific stuff is written in C++, but bindings to Python, Java, I think almost every popular language has bindings to it, Rust, Go, and certainly Haskell has some, I guess, not that mature bindings to it. The advantage of trying to do this kind of stuff with Haskell is that you catch errors at compile time. So as Nick was talking about, very often in processing big data, you're working with distributed systems, and if you're only picking up errors by the time you've actually shipped your code across a distributed network, there's this delay that can be quite frustrating. So this is, I think, a bit of an experiment to see whether Haskell can live up to this promise. But it should, yeah. So just there's some really basic code. It just shows you a visual representation of the computation graph that gets set up. So this slide and a few of the other slides on here are from a presentation that was given by the developers of the Haskell TensorFlow binding. In this one, basically, a tensor is a multidimensional array, usually of some kind of numerical data type. So it could be just a matrix, a vector, or have multiple dimensions. And in this example over here, we basically, each of those lines represents tensor data flowing along that line. Okay? And then each node over here represents either a data source where you get numbers from, or it represents a node that you is going to take some tensor values and do some kind of computation. So in this example, it's going to add two lists of numbers. So the first list of numbers over here, it contains a 3 and a 4, and the next one a 1 and a 1. And when you run this it up, it's a 4 and a 5. Yeah, just give me a shout if you have a question at any point. I'm going to try and race through this, so I should probably speed up again. So in this code that I showed on the first slide, it's quite thin on specifying any of the types. Again, one of the things I like about Haskell is that a lot of the time it actually reads sort of as type-free as code like languages like Python, where you don't have to bother about specifying types. So the types don't clutter up your code, but they're always there. So the compiler is inferring those types every step of the way. And so in this example over here, that's actually the only specification of the type over here. Everything else is inferred. It's a list of numbers. If the first number in the list is a float, then all the other numbers in the list must be a float. Because these two things over here are added, it infers that this must be a list of floats as well. The other thing over here is I'm using the plus operator. That's because the tensor type is an instance of the num type class, which means you can do things like add and multiply using just the natural syntax. So over here, this is essentially the same code. Well, it is actually the same code, but this time with some comments highlighting what the types are. So we're in a monad. I'm not going to try and explain tonight what that is, but just catch me while we have pizzas. The few times that I've explained to people what a monad is, I've realized that from scratch I can explain to someone within an hour. So if you've got an hour, then I can explain to you, and you'll be quite happy that you understand what a monad is by the end of that. Cool. So the session, the TensorFlow session is a monad. Run session basically takes a session monad and gives you back an IO monad, which is why you can equate it with the main over here, which is the starting point of your program. Over here, you'll see what happens if you call this vector function with a list of floats. You get this tensor wrapper. I'm not going to go into detail. There's a link at the end of the slides that explains what this type parameter over here is about, and obviously the float type is what's in there. I've already said that tensor is an instance of the num type class, which is why you can do things like add. Run over here basically takes the tensor and spits out a session. We extract the vector of floats and print it out. Yeah. So just something slightly more complex. It's pretty much the same code. We've added in another one over here just to show you sort of how the graph builds up now. So we hadn't added, now we've got a multiply as well, and we're feeding a constant in there. So yeah, pretty simple to do matrix calculation. And remember that you're going to end up doing these on really high performance hardware, for example, the GPU. There's one more thing that makes this really nice, and that is in machine learning, a big part of what you have to do is you have to find, you have to train a neural network, and that pretty much means finding thousands of numbers that make your computer able to do these things that we think are magical, right? Classify images in a way that we think only humans used to be able to do. And to do that actually requires a bit of calculus, and TensorFlow actually transparently does that. So it knows how to take a derivative with respect to some number and another number if you've got a quantity that is adding those two numbers together. So you just specify all of this, but behind the scenes, if you decide, okay, it's time to do a gradient descent and it needs to do that little bit of calculus, it's all built in for you. Not only is it doing that, it's also doing it in a very efficient way, which is pretty much the key idea in machine learning, which is what's called backpropagation. So again, how many people are familiar with those ideas? Just a quick show of hands. I mean, yeah, so actually quite a lot of people have familiarity with it. So I'm just going to skip past details like that. Feel free to come and chat to me, and I can go into a lot more detail on all of that. So the first example I did is this one over here. It's a simple linear regression. So you've got a whole lot of data points, those little blue dots over there, and you want to fit a straight line to it. A line has this much maths. You hopefully do remember. A line has a slope and an intercept, so that's two numbers. And once you find those two numbers, if you can find the best pair of numbers, then you've got a good fit. And if you've got a bad choice of numbers, then your line might go that way and it doesn't look anything like the data. So you can find that fit using TensorFlow. So good enough to read? I can zoom into it. So at the heart of that bit of code is pretty much this function, which is sort of a mix between pure and code that relies on side effects. And that's something I really should be quite upfront about, is when using TensorFlow through Haskell, you're actually reliant on the IO monad a lot of the time. That's because everything that's happening in the non-Haskell part is a side effect. So the moment you train a neural network, you change all the weights inside that neural network. You had a side effect. On the next line of code, you're now going to use that to make inference, and it's going to use those weights. So you can extract little bits of code here and there that are going to be pure functions, but you tend to be quite heavily reliant on side effects of code, and that tends to be the case with a lot of numerical libraries I find, not just TensorFlow. So over here, yeah, given two lists of numbers, so this will be the x data and this will be the y data. Basically, every point, every one of those blue dots that I showed has an x and y coordinate. A long list of those is a whole lot of blue dots, right? And what I'm going to return is a pair of floats, the slope and the intercept. Inside this TensorFlow session monad, this is how you convert a list of numbers into a TensorFlow vector. Over here, we are the numbers that we're going to hunt for to find the correct value. So we initialize them both to zeros. So that's the slope and the intercept. And pretty much the formula for a straight line, right, is to take the x number and multiply it by the slope and then add on the intercept. This is the interesting part, is that you always define a measure of how badly you're doing. And that's what you're going to try and minimize. Okay, so you're going to fit a straight line. The first guess at that line is going to be lousy, and pretty much every single blue line is going to be every single blue dot is going to be a far distance from that line. So, so the way we're going to measure that is we're going to take the true y value and subtract it from the one we've just calculated using the weight and intercept, and call that the loss. The next thing we do is we minimize that loss. These are the two things we can fiddle with to try and minimize that loss. We're going to use a built-in method in TensorFlow called gradient descent. One of the things it needs to know is the learning rate. I'll explain in detail later if you want to ask me what that is. We run 400 iterations of that training step, and finally we can pretty much read out the values for the slope and the intercept, so that we capture them just as pure numbers over here. So this is pattern matching, well, return them over here, and obviously they can come up. So a slightly more exciting example is this one. Anyone recognize this? Yeah. So like almost every single tutorial, like within the first 3 tutorials, starts out with this example. So on the screen here, each number that's written over here is a handwritten digit. I've actually just squashed a whole lot of them together over here, but just if I cut over there, that would be a 28 by 28 pixel image of a handwritten digit. In this data set, there are 60,000 of these images, and each image there's another file which has 60,000 single digits, which are actually the labels for what that is. So if you feed into your computer program just that list of pixel values, and you want to train it, you also need to tell it, well, I'm expecting over here to see a 5, a 0, a 1, whatever these are. Okay. So this example again from the slides that I mentioned earlier, pretty much each input is 28 by 28. That's 784 pixels. That's what this over here represents. I know there's not 784 circles down the side there. Each input value over here gets multiplied by a number called the weight. That's what that basically would be associated with this line over here. And for every single input, there's a let's start over here. This is what's called a hidden cell, and basically every single pixel value gets multiplied by a weight, which would be associated with each of those lines. And where all these lines join together, they all get added together. And that actually, it turns out, is just matrix multiplication. Okay. And if I've said this is matrix multiplication, then so is this over here. So if you multiply something by a matrix and then multiply by another matrix, you might as well just multiply by one matrix. So in between that, we add in a non-linearity. Otherwise, we just fit in a linear model. And then once we've done that, we want to find a way of, well, after the second multiplication over here, we end up with a list of 10 numbers. Okay. And we want to pick, basically we want the maximum value of that to represent the digit that we think this is. So the way that is done is by using the softmax function, which essentially just converts all these numbers into the range 0 to 1. And scales them so that they total up to 1. So you can interpret it as a probability. We also define a loss function again, which is similar to what I did with the straight line fit. And so this loss function over here is what's called the cross entropy. So turns out that's a good loss function. I can go into more detail if you want, but I'll skip past that. I think I've already spent too much time on the non-Haskell side of things over here, so I'm throwing tomatoes. Thank you very much. Much appreciated. So how does that look? So I decided not to paste the code onto the slide. Okay, so the first thing we do is we basically set up three functions and capture those in this type called the model. So the first one is the training function. Basically, it's going to get a tensor that represents the images. The next one it gets is the tensor that represents the labels, which digit is the correct one. And basically, it doesn't return any number. And whenever you see, remember the session is a monad. Whenever you see a monad that basically returns unit, you know that you're relying on its side effects. So the side effect it has over here is it's now trained the neural network. Okay. When you want to actually get it to do inference, you feed it an image or a whole lot of images, and it basically feeds you back a list of all the labels for the images that you fed in. Okay. And when you want to measure how well it's performing, you feed in, similar to what you did with the training, a whole lot of images, a whole lot of labels for what the correct answer would be. And it spits out a float telling you what the error rate is. So if the error rate is 0, then that's brilliant. If it's 100%, then that's lousy, right? And to create the model, similar thing. It's not all that different from the example I showed a little bit earlier over here, except we've got to add in things like the matrix multiply and the non-linearity that I mentioned, and so on. So we initialize, instead of just the weight and intercept, we initialize a whole lot of numbers over here, which are the hidden weights, the hidden biases, which actually weren't shown on the previous diagram. We calculate the value in the hidden layer by basically doing a matrix multiply of the image vector with the hidden weights, and we add on the biases. Here's the non-linearity. Now we've got to go to the next layer. So the same thing, we need some parameters. These are the weights for the next layer. Exactly the same. These are the biases for the next layer. Exactly the same as we did earlier, a matrix multiply of what comes into that layer, which was the values from the previous layer, by the weights on that layer, and add on the biases over here. And pretty much to make a prediction, we pick out the maximum value after running the softmax, which is built in, like I said. Well, so it's not built in. I mean, it is built in, but I hadn't said it was built in. So brain's starting to scramble sentences at this point over here. Anyway, yeah. So similarly, we want to calculate. Okay, so we want to do the training step over here, and basically we're going to minimize the loss. The loss is defined up here as the softmax cross entropy. The reduced mean over here is actually defined earlier up, but it relies on a built-in function, because what you do is you don't just feed in one image at a time, and you don't try and feed in the entire 60,000 images at a time. So you do this, say, a few hundred images at a time, and then you average up, you total up, and find the average of your score, of your cross-entropy score. So your training step is then to just call this minimize with function. You tell it which minimizer. This is similar to gradient descent with a few modifications. And again, yeah. So I've kind of probably gone into too much detail. I think you get the point, right? So the whole point over here is that you should get some benefit from making sure all the types align. What is interesting is that what I really was looking for when digging into this was something that frustrates me quite a bit when doing this in Python is, well, it blows up when the types don't align, and I only find out later. But the other thing is when for some reason mismatched the tensor sizes. So you might be taking a matrix that's 10 by 10 and trying to multiply it by a vector that's 20 elements long, and that you just can't do that, right? So turns out Haskell doesn't help you in that case, the way I've got it over here. But I've been following along a blog which basically, see if I can find just a so basically what this one does over here is just a simple add again. So you'll see over here it's doing an add, but here all along earlier on I said the types aren't cluttering up the code, and over here certainly the types are cluttering up the code, but for good reason, because what we're trying to demonstrate over here is we can do dependent types in Haskell. And use the type system. So over here it's saying this is a vector with 4 elements in it. And there you can actually see it's creating that from a list. If I try and get that to compile it, as I've written it there, it actually will compile. Okay, so if I've only got 3 numbers in my list, and I actually tell it to put it in a type that's got 4 elements in it, that'll compile fine, and I'll only blow up at runtime. But if over here I tell it to essentially reshape, and this I said was it's a 2 by 3 matrix now. It's expecting 6 numbers, and up here I'm trying to feed in only 4 numbers already. You'll see it's starting to flag the error over there.
So combining 2 tuples on the back, or is template Haskell, right?
It's type dependency in Haskell. Yeah. To be honest, I haven't fully got my head around it, and I probably never will. But yeah, so I've looked at dependent types, and kind of, if anyone's ever heard of Idris or Agda, and I think Daniel's going to mention it later on when he talks about Coq. So dependent types are out there, yeah, like I say, this code over here is actually starting to get some way towards that kind of type safety. Okay, I kind of feel like I don't know if pizza's here already, but yeah. All right, so I better stop. You never want to be the speaker who's between the audience and their pizzas. So let's just take 1 or 2 questions. Yeah.
I have 2 questions.
Yeah.
The one, so other than type safety, is it different all from Python? So I guess is it line by line?
Yeah. So.
Or is it short?
Absolutely not. In some ways, Python is a lot better. So this is the same example, more or less. And I think the point is that Python at the moment is got such wide adoption, and just so many people contributing to it, that they're just way better tutorials, examples, and the code libraries are far more comprehensive. So this is essentially the heart of this is essentially the heart of what we were doing. There's no types in there or anything like that, but 3 lines of code, and it's defined that same model. Everyone's got the stunned look on their face. You can't believe it that those 3 lines of code are equivalent to what I just showed you on the other slide, right? So I think it's quite hard to say, actually, no, I'm going to switch over and try to do everything in Haskell, because you can do that example in 3 lines of code. Well, except for all the 20 lines of code above and below, they're all to do with other aspects like reading in the images and converting stuff like that. But the heart of it has been made really simple in Python. And the bindings from Haskell to TensorFlow are still not complete. So there's still a lot of gaps. There's some aspects in the TensorFlow library that you can't get to from Haskell yet. I think what will happen is over the years, it'll probably catch up. But I think if you want to be at the bleeding edge from the machine learning side, you probably still want to be doing it in Python. Any other question?
I probably forgot myself, but is read value in the TensorFlow import, was that pure function? Because if the input changes, then the output will be different every time, right? Or does the TF mul and add, do they take on the right hand side the second argument to function? Is an IO action, or
No, so it's a tensor, and all of that is happening inside a session monad.
Yeah.
And then to convert that to an I/O action, you have to basically pass that to run session.
So when you do like mile, you just keep changing that thing and then you evaluate it at the end.
Yeah, so you could put lots of nulls one after the other. Yeah. So in fact, that example had it. So it pretty much had, multiply this by that and had that. I can't quite remember what the subtlety is about having to insert read value every now and then.
Yeah,
I'll try to remember.
How does the weight initialization kind of match up with the functional programming philosophy using the random?
So in this example, it just had a simple random initializer. I haven't explored that because if I zoom this in straight from Python, I've got a wide range of options for initializing those weights. Say your initialization, for example, it might be available in those bindings. I'm not sure.
I think kind of the cool thing about this is now you can write your loss function as a pure function, and you're still going to get like efficient matrix arithmetic, which is like not something you like. You could take it for granted, but there's actually a lot going on. So I guess the promising thing about like TensorFlow and functional programming is that we can write like complicated matrix arithmetic in a pure way, which I see like obviously it's a little bit hacky at the moment, but that's kind of the cool thing about this.
Yeah,
right?
I mean, I think the thing about Haskell is that you can write pure functions, but you can also write non-pure functions. And I think what differentiates it from any other language is that the type system actually tells you when you're doing something that may have side effects, and when you're doing something that's pure. There's never a surprise inside the function. So a lot of the time inside just to construct the computational graph, you actually have to do it in the side effecting style. Most of that file was actually side effect style. But that said, again, we're out of time, but it's quite interesting to take one of these examples and actually look at. There were two cases where we did a matrix multiply and add a bias. That's we should really be trying to extract a function there. And I tried that earlier on, and it's quite nice. You end up pretty much with a pure function that you extracted. So it is, you do end up with a lot of pure functions all over your code. I haven't really had enough time to show you a few of the other places where they take slightly more complex constructs and extract them out in pure functions so that you can actually specify how parts of the network connect. And you've just got these pure functions that define the topology of your network. So let's stop there, and feel free to ask any more questions